Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the frozen realm of Saturn's most enigmatic moon, where ice geysers pierce the darkness and ancient waters hide beneath crystalline shells. If you find peace or curiosity in these gentle stories, please consider liking video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the autumn of 2005, the Cassini spacecraft drifts through Saturn's neighborhood like a patient observer, its golden body catching faint sunlight as it approaches the ringed planet's retinue of moons. The spacecraft moves with deliberate grace through the vacuum, its trajectory calculated years in advance by teams of mathematicians and orbital mechanics specialists working with pencil-thin margins of error across billions of kilometers. Among Saturn's 62 known companions orbits Enceladus, a small world wrapped in brilliant white ice, reflecting nearly 99% of the light that touches its surface. For decades, this moon has been little more than a bright dot in telescopes, catalogued and measured but largely ignored in favor of Saturn's larger, more dramatic satellites like cloud-shrouded Titan and crater-scarred Iapetus. The spacecraft's instruments sweep across Enceladus's ice fields with methodical precision, measuring temperatures and magnetic signatures through sensors designed to detect the faintest traces of activity. Cassini carries 12 scientific instruments, each one representing decades of engineering refinement and testing, from magnetometers sensitive enough to detect variations in magnetic field strength measured in nanoteslas to spectrometers capable of identifying individual molecular signatures in vanishingly thin atmospheres. The data streams back to Earth at the speed of light, taking nearly an hour and 20 minutes to traverse the gulf between Saturn and the Deep Space Network antennas scattered across our planet's surface. Something unexpected emerges from those data streams, patterns that don't align with predictions about a small, distant, frozen world. The southern hemisphere of Enceladus registers warmer than it should be, given its position nearly 10 astronomical units from the Sun, where solar energy delivers only 1% of the intensity it provides to Earth. Theoretical models suggest temperatures should plummet to minus 200 degrees Celsius across the moon's surface, cold enough to freeze nitrogen from the air we breathe. Yet patches near its south pole glow with relative warmth in the infrared spectrum, registering temperatures approaching minus 130 degrees Celsius, still brutally cold by terrestrial standards, but nearly 70 degrees warmer than expected in this frozen realm, as if some internal furnace keeps portions of the ice from reaching the bitter equilibrium temperature of deep space. The mystery deepens as Cassini's magnetometer begins detecting subtle disturbances in Saturn's magnetic field whenever the spacecraft passes near this particular moon. The magnetic anomalies suggest the presence of conducting material, perhaps liquid water somewhere within Enceladus's interior, creating electrical currents that interact with Saturn's powerful magnetosphere. These aren't random fluctuations, but consistent, repeatable signatures that grow stronger and weaker in patterns that correlate with the spacecraft's distance from the moon's surface. The first close flyby, planned originally as a routine survey of Saturn's middle-sized moons, transforms into something more significant when Cassini's cameras resolve surface details invisible from greater distances. 4 parallel scars slice across Enceladus's southern region, each fracture stretching for hundreds of kilometers like precise surgical incisions carved into the ice with geometric regularity. Scientists will later name these features the tiger stripes, though their formal designations carry the more prosaic labels of Alexandria, Baghdad, Cairo, and Damascus sulci geographic references that somehow seem inadequate for features existing on an alien world circling a distant gas giant. These aren't mere cracks formed by thermal expansion and contraction, the kind of surface fractures common on frozen worlds throughout the outer solar system. Close examination reveals active geological processes. The fractures' surfaces measure conspicuously warmer than surrounding terrain, their edges sharp and well-defined rather than softened by eons of micrometeorite bombardment and space weathering. The tiger stripes appear fresh, geologically speaking, as if they formed recently or experience ongoing renewal that erases the accumulated damage of cosmic time. Each stripe runs roughly parallel to its neighbors, separated by distances of approximately 35 kilometers, suggesting some underlying structural control governs their formation and evolution. The realization dawns slowly. Transmitted across nearly 1.5 billion kilometers of space in radio waves that carry digitized images and spectral data, this small moon, barely 500 kilometers in diameter, smaller than the state of Texas, harbors some form of geological activity that contradicts conventional wisdom about planetary evolution. Worlds this small should have lost their internal heat billions of years ago, their cores cooling and solidifying into inert rock and metal. Yet something keeps Enceladus warm enough to fracture its ice shell and maintain active surface features. As Cassini continues its orbital ballet around Saturn, returning repeatedly to study Enceladus with each passing month, the instruments detect something even more remarkable streaming away from those mysterious tiger stripes. Material fountains upward from the fractures in thin, ghostly plumes that rise hundreds of kilometers above the surface before dispersing into the vacuum of space. Water vapor forms the primary component of these ethereal eruptions, accompanied by ice particles ranging from microscopic crystals to chunks several centimeters across, along with trace amounts of other substances that will require years of analysis to identify and understand. The plumes create a tenuous atmosphere around a world that should possess no atmosphere at all, its gravitational field too weak to retain gases, its distance from the sun too great to drive atmospheric processes through solar heating. Yet there it streams, visible in backlit photographs as gossamer curtains of material arcing gracefully away from the surface, like frozen waterfalls flowing upward into the cosmic dark. The small moon breathes through these icy wounds, exhaling material that has traveled from somewhere deep within its interior, carrying chemical signatures of processes occurring in realms no human instrument has directly observed. Only a world 1/7 the diameter of Earth's moon, possessing such unexpected geological vigor, the discovery challenges fundamental assumptions about where active processes might occur in the outer solar system, suggesting that size and distance from the sun may not wholly determine a world's capacity for change and renewal. Enceladus operates according to its own schedule, indifferent to theoretical predictions based on larger, more obvious worlds. The tiger stripes continue their quiet exhalations, patient fountains that have likely operated for millions of years, noticed only when human technology finally developed the sensitivity to detect their whispered presence across the interplanetary void. The tiger stripes reveal themselves gradually through repeated observations, their geometric precision becoming more apparent with each flyby as Cassini's instruments map their dimensions and characteristics. Alexandria Sulcus stretches longest among the four parallel fractures, extending nearly 180 kilometers across Enceladus's southern terrain like a surgical incision made by some cosmic scalpel. Its companions, Baghdad, Cairo, and Damascus, run parallel courses separated by remarkably consistent distances, as if some underlying structural framework dictates their placement with mathematical regularity. Each stripe measures between 2 and 4 kilometers wide, their walls rising several hundred meters above the surrounding ice plains in ridged formations that catch shadows in the oblique lighting of Saturn's distant sun. The fractures cut through some of the youngest terrain on Enceladus's surface, regions where the ice appears smooth and relatively uncratered compared to the Moon's northern hemisphere. Crater counting, that fundamental tool of planetary geology, suggests the southern plains formed within the last 100 million years, recent by solar system standards, though still encompassing a span of time that dwarfs the entire history of complex life on Earth. The taiga stripes themselves appear even younger, their sharp-edged profiles unmarked by the gentle softening that accompanies eons of micrometeorite impacts and cosmic ray bombardment. Some researchers propose these features may be less than 10 million years old, practically newborn in geological terms. Thermal imaging reveals the stripes' most striking characteristic: they glow with internal warmth, like heated coils embedded in an otherwise frozen landscape. While the surrounding ice fields maintain temperatures around -200 degrees Celsius, measurements along the fractures register readings approaching -70 degrees, still brutally cold, but more than 100 degrees warmer than their surroundings. The heat distribution isn't uniform along each stripe's length. Instead, it concentrates in discrete hotspots that align with areas of maximum plume activity, as if the fractures breathe more heavily at certain locations. The warming occurs from below, conducted upward through kilometers of ice from some internal heat source that researchers are only beginning to understand. Traditional models of planetary thermal evolution suggest that Enceladus should have exhausted its primordial heat billions of years ago, its small mass insufficient to retain the nuclear decay products and accretional energy that keep larger worlds geologically active. Yet something continues to pump energy into the Moon's interior, maintaining temperatures high enough to keep water liquid beneath the frozen shell and drive the complex processes that fracture the surface along these precise geometric lines. Crystallographic analysis of the ice surrounding the taiga stripes reveals a complex history of freezing and refreezing, as if liquid water periodically wells up from below and solidifies in successive layers. The crystal structures show evidence of rapid cooling, alternating with periods of gradual temperature change, creating distinctive patterns that researchers compare to tree rings, each layer recording environmental conditions during its formation. Some crystals preserve evidence of dissolution and recrystallization, suggesting that liquid water sometimes flows along the fracture walls before freezing solid, leaving behind mineral deposits and altered ice formations. The stripes' parallel arrangement puzzles planetary scientists accustomed to more chaotic patterns of surface deformation. On most worlds, tectonic fractures follow the path of least resistance, creating irregular networks of cracks that branch and merge like river systems or shattered glass. Enceladus's taiga stripes maintain their geometric discipline across hundreds of kilometers, their spacing and orientation suggesting some form of organized stress pattern controls their development. Computer models propose various mechanisms: global tidal forces from Saturn's gravity, convective patterns in the subsurface ocean, or resonant vibrations in the ice shell itself. Each stripe exhibits subtle individual characteristics that distinguish it from its neighbors, like siblings sharing family resemblances while maintaining distinct personalities. Alexandria shows the most consistent thermal output along its length, with relatively little variation in temperature or plume intensity from one monitoring session to the next. Baghdad demonstrates more erratic behavior, sometimes producing vigorous eruptions that dwarf its usual output, then subsiding to barely detectable levels of activity. Cairo maintains intermediate characteristics between its more dramatic neighbors, while Damascus often appears as the quietest of the four, though even its modest emissions exceed anything detected from other regions of the Moon's surface. The fractures penetrate deep into Enceladus's ice shell, their roots extending far below the limits of direct observation. Seismic modeling based on the mechanics of similar features on Earth suggests the cracks may reach depths of several kilometers, possibly extending through the entire thickness of the frozen crust to make direct contact with the liquid ocean beneath. This connection would explain how material from the hidden sea finds its way to the surface, carried upward by pressure differentials and thermal convection through fracture networks that function like planetary circulatory systems. Repeated observations reveal that the tiger stripes experience cyclic variations in their thermal output and plume activity, patterns that correlate with Enceladus's elliptical orbit around Saturn. As the Moon swings closer to the giant planet, tidal forces intensify, squeezing and flexing the ice shell with increasing vigor. The fractures respond by opening slightly, allowing more material to escape from below and creating the spectacular eruptions that Cassini observes during each close approach. When Enceladus retreats to the more distant portions of its orbit, tidal stresses relax, the fractures partially close, and plume activity diminishes to lower baseline levels. The tiger stripes represent active geology on a world that theory suggests should be inactive, their patient exhalations continuing a process that may have operated for millions of years before human instruments arrived to witness and measure their performance. They slice across the southern ice fields with geometric precision, marking the locations where Enceladus's hidden ocean announces its presence to the cosmos through fountains of water and ice that rise like prayers into the darkness between worlds. 4 parallel wounds in the frozen surface, each one a window into processes occurring in realms far below the reach of direct observation. The plumes rise from the tiger stripes like ethereal waterfalls flowing in reverse, their gossamer streams visible only when backlit by Saturn's distant sun or illuminated by the reflected glow from the planet's immense ring system. Each eruption begins deep within the fractures, where pressurized water and vapor escape through networks of interconnected cracks and channels carved into the ice shell over geological time. The material accelerates upward through these conduits, driven by pressure differentials that exist between the subsurface ocean and the vacuum of space, creating fountain-like displays that dwarf any geyser phenomenon found on Earth. Cassini's instruments detect dozens of individual jets streaming from specific locations along the tiger stripes, each one following a ballistic trajectory determined by Enceladus's weak gravitational field and the initial velocity imparted by the eruption process. The largest plumes achieve heights approaching 500 kilometers above the surface, nearly twice the altitude of the International Space Station above Earth, before the material begins to fall back toward the Moon or escapes entirely into Saturn's magnetosphere. Smaller jets reach more modest elevations, creating a tiered display of activity that varies in intensity with the tidal stresses imposed by Saturn's gravitational influence. The composition of these ethereal eruptions tells a story of hidden chemistry occurring in realms far beneath the frozen surface. Water vapor forms the primary constituent, comprising roughly 90% of the material detected by mass spectrometry, but the remaining 10% reveals a complex mixture of substances that speak to active processes in the subsurface ocean. Nitrogen, carbon dioxide, methane, and hydrogen emerge from the depths, along with trace amounts of ammonia, hydrogen sulfide, and simple organic compounds that suggest chemical reactions occurring in the liquid reservoir below. Ice particles accompany the vapor in a wide range of sizes, from microscopic crystals barely larger than molecules to chunks several centimeters across that tumble through space like tiny asteroids. The size distribution follows patterns that researchers recognize from terrestrial geysers and volcanic eruptions, Most particles measure less than a micrometer in diameter, while progressively fewer examples exist at larger sizes, creating a statistical signature that reveals information about the eruption mechanism and the conditions existing within the source region. The largest particles require the most energetic ejection processes to achieve escape velocity, suggesting that some plumes operate under higher pressure conditions than others. Spectroscopic analysis reveals that the ice particles aren't simply frozen water, but contain inclusions of dissolved materials that provide chemical fingerprints of the ocean's composition. Salt crystals embedded within the ice grains indicate that Enceladus's hidden sea contains dissolved sodium chloride and other minerals in concentrations that approach those found in Earth's oceans. Sulfur-bearing compounds suggest interactions between the liquid water and rocky material, possibly indicating hydrothermal processes occurring at the ocean floor where hot water circulates through mineral-rich sediments. The plumes create Enceladus's thin atmosphere, a ghostly envelope of water vapor and other gases that extends several hundred kilometers above the surface before dissipating into the vacuum surrounding Saturn. This tenuous atmosphere varies in density with the level of plume activity, thickening when tidal forces enhance eruption intensity and thinning during periods of reduced geological activity. The atmospheric pressure at Enceladus's surface measures less than 1/1000th of Earth's atmospheric pressure, so rarefied that it would be considered a laboratory vacuum by terrestrial standards, yet dense enough to create observable effects on spacecraft instruments and produce subtle hazes visible in high-resolution photography. Much of the material ejected by the plumes escapes Enceladus entirely, carried away by Saturn's magnetic field and distributed throughout the giant planet's magnetosphere. These escaped particles contribute to Saturn's E-ring, a gossamer structure that extends from the orbit of Mimas to beyond the orbit of Titan, fed primarily by the continuous exhalations from Enceladus's tiger stripes. The ring material consists almost entirely of water ice particles with sizes measured in micrometers, creating a nearly invisible extension of Saturn's more prominent rings that can only be detected through careful analysis of scattered sunlight and charged particle interactions. Computer modeling suggests that the plume eruptions operate under conditions similar to those found in terrestrial geysers, where underground reservoirs of superheated water flash to steam when pressure suddenly decreases. On Enceladus, the mechanism likely involves liquid water stored in chambers within the ice shell, heated by tidal friction and pressurized by the weight of overlying material. When fractures open pathways to the surface, the water explosively boils and expands, driving the spectacular fountains that Cassini observes with each flyby of the small moon. The eruption velocities vary significantly among different plume sources, ranging from barely sufficient to lift material a few kilometers above the surface to energetic enough to accelerate particles beyond Enceladus's escape velocity of only 240 meters per second, roughly the speed of a well-thrown baseball. This range suggests that the subsurface plumbing system includes reservoirs at various depths and pressures, some connected directly to the global ocean, while others tap intermediate chambers where water has partially cooled and depressurized during its journey toward the surface. Each plume carries material that has traveled through kilometers of ice, potentially spending thousands of years in transit from its origin in the subsurface ocean to its explosive release into space. The journey may alter the chemical composition through interactions with the surrounding ice, dissolution and precipitation of minerals, and exposure to radiation from Saturn's magnetosphere that penetrates the upper layers of the ice shell. What emerges in the plumes represents a processed sample of the ocean's contents, chemically modified by its passage through the complex geological systems that connect Enceladus's hidden sea to the vacuum of space. The plumes continue their patient displays, rising and falling with the rhythms of orbital mechanics and tidal forces, carrying messages from the deep ocean in languages of ice and vapor that human instruments are only beginning to decode. They stream upward like frozen prayers. Each eruption a brief announcement of the active processes occurring in the darkness beneath Enceladus's brilliant surface, where liquid water has persisted for possibly billions of years in seas that have never known sunlight. Beneath the fractured ice shell of Enceladus lies an ocean that may contain more liquid water than all of Earth's seas combined. A realization that emerges gradually from years of careful gravitational measurements and orbital mechanics calculations. Cassini's repeated flybys create a detailed map of the Moon's gravitational field, revealing subtle variations that indicate how mass distributes within the small world's interior. The spacecraft's radio signals, tracked with precision measured in millimeters per second, betray the presence of dense material beneath the southern hemisphere and lower density regions that suggest substantial volumes of liquid water hiding beneath the frozen surface. The gravitational data paint a picture of internal structure that contradicts initial assumptions about small, icy moons. Rather than a solid ball of rock and ice frozen throughout, Enceladus maintains a differentiated interior with a rocky core surrounded by a global ocean that extends beneath the entire ice shell. The ocean depth remains uncertain, but estimates suggest it ranges from 30 to 40 kilometers, in some regions deeper than Earth's Mariana Trench, while maintaining an average depth of perhaps 25 kilometers across the Moon's entire surface. This hidden sea contains roughly twice the volume of water found in Earth's oceans, locked beneath an ice shell that varies from less than 5 kilometers thick at the South Pole to perhaps 25 kilometers thick in equatorial regions. The ocean's existence defies conventional wisdom about planetary thermal evolution and the conditions necessary to maintain liquid water in the outer solar system. At Enceladus's distance from the Sun, solar heating provides negligible energy input, less than 1% of the energy that Earth receives per unit area. Without some internal heat source, any water should have frozen solid billions of years ago, creating a homogeneous ball of ice and rock with no geological activity or atmospheric phenomena. Yet, the gravitational measurements confirm that substantial volumes of liquid water persist within this small world, maintained by heat sources that continue operating long after primordial warmth should have dissipated into space. Chemical analysis of the plume materials provides additional evidence for the ocean's composition and the processes occurring within its lightless depths. The sodium chloride detected in ejected ice particles indicates salinity levels that approach those found in terrestrial seawater, suggesting that the hidden ocean contains dissolved minerals leached from the rocky seafloor over geological time. The salt concentrations imply long-term chemical equilibrium between liquid water and solid rock, a process that requires sustained contact between these materials under conditions warm enough to promote dissolution and ion exchange. Sulfur compounds identified in the plume chemistry point toward more complex interactions occurring at the ocean-rock interface. On Earth, similar chemical signatures often indicate hydrothermal activity, where heated water circulates through mineral-rich sediments or fractured bedrock, extracting dissolved materials that alter the fluid's composition. The presence of hydrogen sulfide and other sulfur-bearing molecules in Enceladus's plumes suggests analogous processes may operate on the floor of the hidden ocean, where tidal heating and radioactive decay create temperature gradients that drive convective circulation and chemical reactions. The ocean's global extent, confirmed through gravity field analysis, means that Enceladus's liquid water reservoir maintains contact with rocky material across the entire seafloor rather than existing as isolated pockets within the ice shell. This geometry maximizes the potential for water-rock interactions and chemical exchange processes that could create the complex chemistry detected in the plume emissions. The seafloor likely consists of hydrated minerals, clays, and possibly serpentinized rocks similar to those found in Earth's oceanic crust. Materials that form through the interaction of liquid water with silicate minerals under moderate temperature and pressure conditions. Temperature estimates for the ocean vary depending on the modeling assumptions, but most calculations suggest liquid water temperatures ranging from slightly below freezing near the ice shell interface to perhaps 4 degrees Celsius in the deepest regions where tidal heating effects concentrate most strongly. These temperatures fall within ranges that support liquid water chemistry and potentially biological processes, though the absence of dissolved oxygen and the high salt concentrations create environmental conditions unlike those found in most terrestrial aquatic ecosystems. The ocean's chemical stratification remains poorly understood. Though theoretical models suggest that convective circulation driven by tidal heating may create well-mixed conditions throughout much of the water column, dissolved materials entering the ocean through hydrothermal processes at the seafloor would circulate upward through convective currents, eventually reaching the ice shell where some fraction gets incorporated into the solid matrix or ejected through the plume systems. This circulation pattern would distribute heat, dissolved minerals, and any potential biological signatures throughout the ocean volume rather than allowing them to remain concentrated near their sources. Pressure conditions within the ocean reach levels approaching 50 times Earth's atmospheric pressure at the deepest points, creating an environment similar to the deepest trenches in terrestrial oceans. These pressures are insufficient to significantly alter water's properties or compress the liquid to densities much different from surface conditions on Earth, but they do affect the solubility of various compounds and the stability of different mineral phases that might exist on the sea floor. The pressure gradients also influence convective patterns and the efficiency of heat transfer processes that maintain the ocean's liquid state. The discovery of organic compounds in the plume materials raises questions about the ocean's potential to support complex chemistry or even biological processes. Simple carbon-bearing molecules like methane, carbon dioxide, and formaldehyde emerge from the depths, along with more complex species that include nitrogen-bearing compounds and possibly amino acid precursors. These organic materials could form through abiotic chemical reactions between dissolved carbon dioxide, nitrogen, and hydrogen under the reducing conditions that likely exist in the subsurface ocean. Or they could represent biological signatures if life has evolved within this alien sea. The hidden ocean maintains its liquid state through a delicate balance of tidal heating, radioactive decay, and thermal insulation provided by the overlying ice shell. Computer simulations suggest that this balance has persisted for millions or possibly billions of years, creating one of the most stable aquatic environments in the solar system despite existing in the frozen realm beyond Mars's orbit. The ocean endures in darkness, never touched by sunlight, sustained by gravitational forces and internal heat sources that operate according to the fundamental laws of physics rather than the biological processes that have shaped Earth's surface waters. Enceladus carries its ocean through space like a cosmic arc, preserving liquid water in quantities that exceed Earth's hydrosphere while maintaining chemical conditions that permit complex molecular interactions. The hidden sea sloshes beneath the ice shell with each tidal cycle, its currents and chemistry responding to gravitational forces transmitted across hundreds of millions of kilometers from Saturn's massive bulk, creating an aquatic world that exists entirely independent of solar energy and the conditions that govern surface environments on terrestrial planets. Saturn's gravitational embrace shapes Enceladus with invisible hands, kneading the small moon's interior like a cosmic baker working dough through cycles of compression and expansion that repeat with mathematical precision every 33 hours. The giant planet's immense mass, 95 times greater than Earth's, creates tidal forces that flex Enceladus's rocky core and ice shell as the moon follows its elliptical orbit through the Saturnian system. These forces generate internal friction that converts orbital mechanical energy into heat, warming the moon's interior and maintaining liquid water in realms that should remain frozen at temperatures approaching absolute zero. The tidal heating mechanism operates through a phenomenon that physicists call viscoelastic deformation, where solid materials behave like thick fluids when subjected to cyclical stress over geological timescales. As Enceladus approaches the closest point in its orbit, Saturn's gravity pulls more strongly on the near side of the Moon than the far side, creating a tidal bulge that elongates the small world by several meters along the Saturn-facing axis. When the Moon swings to the most distant portion of its orbital path, the tidal forces weaken, allowing Enceladus to relax back toward a more spherical shape. This constant flexing generates heat through internal friction, much like repeatedly bending a paperclip until it becomes warm to the touch. The elliptical shape of Enceladus's orbit amplifies the tidal heating effects by creating larger variations in gravitational stress than would occur in a perfectly circular path around Saturn. The orbital eccentricity measuring approximately 0.0047, meaning the orbit deviates only slightly from a perfect circle, may seem negligible by terrestrial standards, but it proves sufficient to drive the heating processes that maintain geological activity on this distant world. Computer models suggest that a completely circular orbit would reduce tidal heating by more than half, potentially allowing the subsurface ocean to freeze and ending the plume activity that makes Enceladus so remarkable among Saturn's moons. The heating distribution within Enceladus concentrates most strongly in the Moon's rocky core and the lower portions of the ice shell, where tidal stresses encounter the greatest resistance from solid materials. Theoretical calculations indicate that the core may experience temperature increases of several degrees during each orbital cycle, while the ice shell undergoes more modest warming that varies with depth and location. The South Polar region appears to receive enhanced heating due to its position relative to the tidal stress patterns, explaining why the tiger stripes and plume activity concentrate in this particular area rather than distributing uniformly across the Moon's surface. Orbital resonances with other Saturnian moons help maintain Enceladus's eccentric orbit despite the circularizing effects of tidal dissipation. The Moon, Diona, orbiting farther from Saturn, exerts gravitational perturbations that prevent Enceladus from settling into a perfectly circular path where tidal heating would diminish significantly. This gravitational relationship creates a 2-1 orbital resonance, where Enceladus completes exactly 2 orbits around Saturn for every 1 orbit completed by Dione, ensuring that the 2 moons regularly align in configurations that maintain orbital eccentricity through their mutual gravitational interactions. The resonance system operates with clockwork precision, having likely persisted for billions of years while slowly evolving as tidal forces gradually alter the orbital parameters of both moons. Enceladus migrates slowly outward from Saturn as tidal interactions transfer rotational energy from the giant planet to the Moon's orbital motion, a process that occurs at rates measured in centimeters per year but accumulates significant effects over geological timescales. Meanwhile, the Moon's rotation has become tidally locked to its orbital period, ensuring that the same hemisphere always faces Saturn and creating permanent asymmetries in the tidal stress patterns. Energy calculations reveal that tidal heating generates approximately 15 gigawatts of power within Enceladus, roughly equivalent to 15 large terrestrial power plants operating continuously. This heat output exceeds the energy input from radioactive decay within the Moon's rocky core by more than an order of magnitude, making tidal dissipation the dominant heat source that maintains geological activity and prevents complete freezing of the subsurface ocean. The heat production varies with orbital position. peaking during closest approach to Saturn and diminishing during the more distant portions of each elliptical cycle. The heating mechanism operates most efficiently in materials that can deform under stress but resist rapid changes in shape, properties that depend on temperature, composition, and crystal structure. Ice near its melting point exhibits ideal viscoelastic characteristics for tidal heating, becoming soft enough to deform under gravitational stress while maintaining sufficient rigidity to generate friction during the deformation process. This creates a positive feedback effect where tidal heating warms the ice toward its melting point, making it more susceptible to further tidal heating and potentially creating runaway warming in localized regions. Thermal modeling suggests that tidal heating creates convective circulation within both the subsurface ocean and the overlying ice shell, distributing heat more efficiently than simple conduction could achieve. Convective currents carry warm material upward from the heated regions, while cooler material sinks to replace it, creating circulation patterns that help maintain uniform temperatures throughout the ocean volume and prevent excessive heating that might destabilize the entire system. These circulation patterns may also contribute to the formation and maintenance of the taiga stripes by creating preferred pathways for heat and material transport within the ice shell. The tidal forces vary not only with orbital position, but also with the complex gravitational interactions among Saturn's multiple moons, creating subtle variations in heating intensity that operate on longer timescales than the basic orbital period. Jupiter's distant gravitational influence and the elliptical orbits of other Saturnian satellites introduce additional perturbations that modulate the tidal stresses experienced by Enceladus over periods measured in decades or centuries rather than hours or days. Laboratory experiments with ice samples under simulated tidal stress conditions help validate the theoretical models of heating efficiency and deformation behavior. Though scaling these results to the conditions existing within Enceladus requires extrapolations across many orders of magnitude in time, pressure, and spatial scale, the experiments confirm that ice can indeed generate substantial heat through viscoelastic deformation, but they also reveal complexities in the heating process that depend on factors like grain size, crystal orientation, and the presence of dissolved impurities that alter the mechanical properties of the solid material. Tidal heating represents one of the most important energy sources for maintaining habitable conditions in the outer solar system, where solar radiation provides insufficient energy to drive geological processes or maintain liquid water. The mechanism operates entirely through gravitational interactions and orbital mechanics, requiring no external energy input beyond the initial angular momentum that established the satellite system billions of years ago. Saturn continues its gravitational massage of Enceladus with patient consistency, generating the heat that keeps an alien ocean liquid beneath the ice, while the small moon orbits through the cosmic cold far beyond the warmth of the distant sun. The salt particles riding within Enceladus's ice plumes carry chemical messages from the deepest regions of the hidden ocean, their crystalline structures preserving evidence of processes occurring at the boundary between liquid water and solid rock far beneath the frozen surface. Mass spectrometry analysis reveals sodium chloride concentrations approaching those found in Earth's seawater, along with traces of potassium, magnesium, and calcium salts that speak to sustained chemical interactions between the ocean and its rocky container. These dissolved minerals didn't simply appear in the water through cosmic coincidence, they accumulated over geological time through the slow dissolution of silicate rocks and the complex chemical reactions that occur when liquid water contacts mineral surfaces under moderate temperature and pressure conditions. The salinity patterns detected in successive plume observations suggest a mature chemical system that has reached approximate equilibrium between dissolution and precipitation processes. Fresh water contacting virgin rock would initially dissolve minerals rapidly, creating solutions with unstable chemical compositions that change quickly over time. The relatively stable salt concentrations measured in Enceladus's plumes indicate that the ocean has existed long enough for these initial transient effects to subside, replaced by steady-state conditions where the rate of mineral dissolution roughly balances the rate of precipitation and chemical exchange. This chemical maturity implies an ocean age measured in millions or possibly billions of years, rather than the thousands of years that might characterize a recently formed water body. Sulfur-bearing compounds identified within the ejected materials provide additional clues about the chemical environment existing at the ocean floor. Hydrogen sulfide, sulfur dioxide, and various sulfate minerals emerge from the plumes in concentrations that suggest active sulfur chemistry driven by interactions between seawater and sulfur-rich minerals within Enceladus's rocky core. On Earth, similar chemical signatures often indicate hydrothermal activity where heated groundwater or seawater circulates through fractured bedrock, leaching sulfur compounds and other dissolved materials that alter the fluid's composition and create distinctive mineral deposits. The presence of these sulfur compounds hints at reducing chemical conditions within the subsurface ocean, environments where dissolved oxygen remains scarce, and chemical reactions proceed through pathways that differ significantly from those operating in Earth's oxygenated surface waters. Reducing conditions favor the formation of hydrogen sulfide, methane, and other molecules that would rapidly oxidize in the presence of free oxygen, creating a chemical environment more similar to Earth's deep ocean hydrothermal vents than to shallow marine ecosystems. These conditions could support chemosynthetic processes, where microorganisms derive energy from chemical reactions rather than photosynthesis, though no direct evidence for biological activity has yet been confirmed. Trace element analysis reveals a complex mixture of dissolved metals that further supports the interpretation of active water-rock interactions occurring within the ocean. Iron, manganese, zinc, and other transition metals appear in concentrations consistent with leaching from silicate minerals under mildly acidic to neutral pH conditions. The metal concentrations remain relatively low compared to highly acidic hydrothermal systems, suggesting that Enceladus's ocean maintains chemical conditions compatible with the stability of liquid water and the dissolved salt concentrations detected in the plume materials. The spatial distribution of different chemical signatures within individual plume eruptions provides insights into the ocean's internal structure and circulation patterns. Some jets carry higher concentrations of dissolved materials than others, possibly indicating that different plume sources tap water masses with distinct chemical histories or residence times within the ocean system. Computer models suggest that convective circulation driven by tidal heating creates complex flow patterns that could segregate water masses with different chemical compositions, allowing some regions to maintain contact with the seafloor while others circulate primarily within the upper ocean layers. Isotopic ratios measured in the water vapor and dissolved materials offer additional constraints on the processes governing ocean chemistry. The ratio of different sulfur isotopes reflects the balance between biological and abiotic sulfur cycling processes, though interpreting these signatures requires careful consideration of the chemical pathways available under Enceladus's unique environmental conditions. Similarly, carbon isotope ratios in the organic compounds detected within the plumes could potentially distinguish between biological and abiotic sources of organic matter, though the current measurements remain ambiguous and require additional data for definitive interpretation. The pH of Enceladus's ocean, while not directly measurable through remote sensing, can be estimated from the chemical equilibrium relationships governing the dissolved salt concentrations and the stability of different mineral phases. Theoretical calculations suggest slightly alkaline conditions with pH values ranging from approximately 8 to 10, similar to Earth's seawater, but potentially more basic due to the interaction with silicate minerals, and the absence of carbonic acid formation from atmospheric carbon dioxide. These alkaline conditions would favor the dissolution of silicate minerals, while inhibiting the dissolution of carbonate minerals, creating a chemical environment distinctly different from acidic hydrothermal systems. The temporal stability of the chemical signatures detected in successive plume observations indicates that the ocean's composition remains relatively constant over the timescales accessible to spacecraft monitoring. Variations in salt concentrations and trace element abundances appear to correlate more strongly with changes in plume intensity and tidal stress levels than with secular changes in ocean chemistry, suggesting that the fundamental chemical processes governing seawater composition operate in steady state rather than undergoing rapid evolution. This stability implies that the current chemical conditions have persisted for periods much longer than the duration of the Cassini mission. Organic carbon compounds detected within the plume materials add another layer of complexity to the ocean's chemical inventory. Simple molecules like methane and carbon dioxide could form through abiotic processes involving the reaction of dissolved carbon with hydrogen or hydroxide ions under the reducing conditions that likely exist within the ocean. More complex organic molecules might require additional chemical pathways, possibly involving catalytic surfaces provided by mineral grains or clay particles suspended within the seawater. The chemical evidence suggests that Enceladus's ocean functions as a giant natural laboratory where water-rock interactions proceed under conditions that combine aspects of Earth's deep ocean environments with unique characteristics imposed by the Moon's small size, lack of atmospheric pressure, and sustained heating through tidal forces. The dissolved salt concentrations indicate that substantial volumes of rock have been chemically weathered over geological time, while the sulfur chemistry points toward active hydrothermal processes that continue to modify the ocean's composition through ongoing chemical reactions between seawater and the underlying rocky material. These chemical signatures preserved in ice crystals ejected from tiger stripe fractures represent samples of an alien ocean that has never known sunlight, sustained by gravitational forces and chemical energy rather than biological processes or solar heating. The salts carry stories of dissolution and precipitation, of chemical equilibrium achieved through millions of years of patient interaction between liquid water and solid rock in the darkness beneath Enceladus's brilliant frozen surface, where chemistry proceeds according to fundamental physical principles that operate identically throughout the cosmos. The organic molecules detected within Enceladus's plume materials emerge from the subsurface ocean like chemical messengers carrying news of processes occurring in realms far removed from terrestrial experience. Mass spectrometers aboard Cassini identify a diverse inventory of carbon-bearing compounds, ranging from simple two-atom molecules like carbon monoxide to complex species containing dozens of atoms arranged in intricate three-dimensional structures. Methane appears in concentrations exceeding 1% of the total plume composition, while carbon dioxide, formaldehyde, acetylene, and propane create a chemical cocktail that speaks to active organic synthesis occurring within the hidden ocean's depths. These organic compounds don't simply represent contamination from cosmic dust or debris accumulated during Enceladus's journey through space. Their isotopic signatures and molecular characteristics indicate formation through processes occurring within the Moon's interior, where carbon-bearing materials interact with liquid water, dissolved hydrogen, and mineral surfaces under the unique pressure and temperature conditions existing in the subsurface ocean. The detection of nitrogen-bearing organic species like hydrogen cyanide and acetonitrile suggests that nitrogen chemistry also operates within this alien sea, creating molecular complexity that approaches the threshold where simple chemical systems begin to exhibit behaviors associated with prebiotic chemistry. Simple methane formation can occur through several pathways that don't require biological processes, including the reaction of carbon dioxide with hydrogen gas in the presence of metallic catalysts or mineral surfaces that facilitate chemical bond rearrangement. Under the reducing conditions that likely exist within Enceladus's ocean, dissolved carbon dioxide could react with hydrogen produced through water-rock interactions or radiolysis of water molecules by energetic particles from Saturn's magnetosphere. The reaction requires specific temperature and pressure conditions along with appropriate catalytic materials, suggesting that methane production occurs in localized regions where these requirements converge. More complex organic molecules present greater challenges for abiotic formation mechanisms, though several pathways could operate under the chemical conditions inferred for Enceladus's ocean. Formaldehyde synthesis can proceed through the reaction of methanol with dissolved oxygen species, while acetylene formation might involve the decomposition of more complex hydrocarbon precursors under the influence of radiation or high-energy chemical reactions. The presence of these molecules indicates that carbon chemistry within the ocean extends beyond simple one-carbon compounds to include species with multiple carbon atoms linked by covalent bonds. The detection of sulfur-bearing organic compounds adds another dimension to the chemical complexity, suggesting interactions between organic carbon and the sulfur chemistry associated with water-rock interactions at the ocean floor. Molecules like methanethiol and dimethyl sulfide could form through reactions between simple organic species and hydrogen sulfide or other sulfur compounds produced during hydrothermal processes. These sulfur-organic hybrid molecules are particularly interesting because they represent chemical bridges between the inorganic geochemistry of rock-water interactions and the organic chemistry that might eventually lead to more complex molecular systems. Nitrogen incorporation into organic molecules requires specific chemical pathways that can operate under the conditions existing within Enceladus's ocean. Ammonia dissolved in the seawater could react with simple organic compounds to form amino group-containing species, while hydrogen cyanide might polymerize under appropriate conditions to create more complex nitrogen-rich molecules. The presence of both simple and moderately complex nitrogen-bearing organic compounds suggests that multiple formation pathways operate simultaneously within the ocean, creating a diverse molecular inventory through parallel chemical processes. The concentration levels of different organic species provide insights into the relative efficiency of various formation mechanisms and the chemical equilibrium conditions governing organic synthesis within the ocean. Methane dominates the organic inventory by several orders of magnitude, consistent with its formation through relatively simple and thermodynamically favorable reaction pathways. More complex molecules appear in progressively lower concentrations, following patterns that suggest kinetic limitations rather than thermodynamic constraints control their abundance levels. Potential biological origins for the organic compounds remain speculative given the current data, though some molecular characteristics could be consistent with metabolic processes if life has evolved within Enceladus's ocean. The isotopic ratios of carbon and nitrogen in the organic molecules don't yet provide definitive evidence for or against biological formation, partly because the expected signatures depend on the specific metabolic pathways that hypothetical organisms might employ under the unique environmental conditions existing within the subsurface ocean. The spatial and temporal variations in organic compound concentrations within different plume observations suggest that organic synthesis occurs in discrete regions of the ocean rather than uniformly throughout the entire water volume. Some plume jets carry significantly higher concentrations of complex organic molecules than others, possibly indicating that chemical processes concentrate in areas where specific environmental conditions favor organic formation. These variations could reflect differences in temperature, pressure, mineral composition, or residence time that affect the efficiency of organic synthesis reactions. Laboratory experiments attempting to reproduce Enceladus-like conditions have successfully synthesized some of the simpler organic compounds detected in the plumes, confirming that abiotic formation mechanisms can operate under the inferred chemical conditions. High-pressure reactions between carbon dioxide, hydrogen, and various mineral catalysts produce methane, formaldehyde, and other simple organic species at rates consistent with the concentrations observed in the plume materials. However, these experiments have not yet achieved the synthesis of the more complex molecules detected by Cassini, suggesting that additional factors or reaction pathways may be required. The organic chemistry occurring within Enceladus's ocean represents a natural experiment in molecular complexity development under conditions vastly different from those that governed organic synthesis on early Earth. The absence of atmospheric oxygen, the high salt concentrations, the specific temperature and pressure regime, and the unique mineral assemblages available for catalytic reactions create a chemical laboratory unlike any terrestrial environment. The organic molecules emerging in the plumes provide glimpses into this alien chemistry, revealing processes that operate according to the same fundamental principles governing chemical bonding and thermodynamics throughout the universe, while producing molecular diversity shaped by the specific conditions existing within this particular ocean world. The detection of these organic compounds transforms Enceladus from a geologically interesting ice world into a location where complex chemistry creates molecular building blocks that approach the complexity threshold where chemical evolution might begin to operate. The organic inventory emerging from the tiger stripes represents chemical potential energy stored in molecular bonds, created through processes that concentrate carbon, hydrogen, oxygen, nitrogen, and sulfur into increasingly complex arrangements that encode information about the environmental conditions and chemical pathways operating within one of the solar system's most intriguing hidden oceans. The brilliant surface of Enceladus presents a deceptive facade that conceals the true complexity of processes occurring within the moon's interior. Its pristine white ice, reflecting nearly all incident sunlight, while masking evidence of the ancient ocean that has persisted beneath for possibly billions of years. The surface appears remarkably young by solar system standards, with crater densities indicating an average age of less than 100 million years across much of the terrain, a geological infant compared to the heavily cratered highlands of Earth's moon or the ancient impact basins scarring Mars and Mercury. This apparent youth results from continuous resurfacing processes that erase accumulated impact damage, creating an ice shell that appears fresh and unmarked despite the moon's 4 billion-year history. Spectroscopic analysis reveals ice composition dominated by nearly pure water, with trace amounts of other materials concentrated primarily in the fracture systems and areas of recent geological activity. The high albedo measuring approximately 0.99, meaning the surface reflects 99% of incident light, indicates that space weathering processes operate slowly on Enceladus compared to other airless bodies in the solar system. Cosmic ray bombardment and micrometeorite impacts typically darken exposed surfaces over geological time by creating radiation-damaged materials and implanting foreign substances. Yet Enceladus maintains its brilliant appearance through mechanisms that continuously refresh the surface composition. The resurfacing processes operate through multiple mechanisms that work together to maintain the moon's youthful appearance. Plume fallout deposits fresh ice across large areas of the surface, particularly in the southern hemisphere where tiger stripe activity concentrates most heavily. Each eruption cycle delivers tons of pristine water ice that settles onto the existing terrain, gradually building up layers that bury older, more heavily damaged surface materials beneath accumulations of clean, crystalline ice. Computer models suggest that plume deposition rates could completely renew the surface composition within timescales of 10 to 100 million years, consistent with the observed crater retention ages. Thermal cycling driven by Enceladus's orbital variations creates additional resurfacing effects through sublimation and redeposition of surface ice. As the Moon swings through its elliptical orbit, surface temperatures vary by several degrees Celsius, causing ice to sublime directly from solid to vapor phase during warmer periods and redeposit during cooler intervals. This process preferentially removes older, radiation-damaged ice while depositing fresh crystalline material, creating a natural purification mechanism that maintains surface brightness and chemical purity over extended periods. The apparent surface youth obscures evidence of much older geological processes that shaped Enceladus's internal structure during the early phases of solar system evolution. The differentiated interior, with its distinct rocky core and overlying ocean, required millions of years to develop through gravitational settling and thermal evolution processes that occurred during the Moon's first few 100 million years. Radiometric heating from short-lived isotopes like aluminum-26 provided the energy necessary to melt initial ice rock mixtures and drive the chemical separation that created the layered structure observed today through gravitational field measurements. Impact crater analysis reveals that different regions of Enceladus experience varying rates of geological modification, with the northern hemisphere preserving more evidence of ancient bombardment than the heavily modified southern plains. This hemispheric dichotomy suggests that resurfacing processes operate more efficiently in regions where subsurface heat flow and plume activity concentrate most strongly. The northern terrains may provide glimpses into Enceladus's deeper geological history, preserving surface features that formed during earlier epochs when the Moon's internal heat budget and geological activity patterns differed from current conditions. Detailed mapping of surface textures and morphological features reveals subtle evidence of processes that operate over much longer timescales than the dramatic plume eruptions. Ridge systems, groove networks, and linear fractures extend across hundreds of kilometers with orientations that suggest formation through global-scale stress patterns related to tidal flexing and thermal evolution. These features likely developed over millions of years through gradual accumulation of deformation, creating structural frameworks that influence the location and orientation of more recent geological activity, including the taiga stripes themselves. The ice shell's internal structure remains largely hidden beneath the bright surface, though theoretical models suggest a complex architecture of convective cells, thermal boundary layers, and compositional gradients that evolved through interactions between tidal heating, heat conduction, and chemical exchange with the underlying ocean. Seismic waves generated by tidal stresses or impact events could potentially provide information about subsurface structure, but the lack of seismic monitoring equipment on Enceladus limits direct investigation of the ice shell's internal properties and evolution history. Crystallographic analysis of ice samples ejected in the plumes reveals evidence of multiple formation and modification episodes, with some crystals preserving structures that indicate rapid cooling from liquid water, while others show signs of gradual recrystallization under solid-state conditions. The diversity of crystal structures suggests that ice formation within Enceladus occurs through various pathways operating under different temperature and pressure conditions, from explosive boiling during plume eruptions to slow freezing within subsurface chambers and fracture networks. Chemical mapping of surface materials reveals subtle variations in composition that correlate with geological features and proximity to areas of active plume emission. Regions near the taiga stripes show enhanced concentrations of dissolved materials that have been deposited through plume fallout, creating chemical gradients that extend for hundreds of kilometers from the primary emission sources. These compositional variations provide indirect evidence for the chemical diversity existing within the subsurface ocean and the efficiency of material transport processes that connect the hidden sea to the visible surface. The false youth of Enceladus's surface exemplifies how active geological processes can obscure the deep time history of planetary bodies, creating appearances that mislead casual observation while concealing the complex evolutionary pathways that shaped internal structure and chemical composition. The bright, seemingly pristine ice fields hide evidence of ancient bombardment events, early thermal evolution, and the gradual development of the differentiated interior that now sustains one of the solar system's most intriguing hidden oceans. Beneath the deceptive surface lies a 4 billion-year history of gravitational evolution, chemical differentiation, and thermal processes that created the conditions necessary for maintaining liquid water in the frozen realm beyond Mars' orbit. The ice shell serves simultaneously as insulation that preserves the subsurface ocean and as a dynamic interface that mediates exchange between the hidden sea and the vacuum of space, its apparent youth masking the ancient processes that continue to operate in the darkness beneath Enceladus's brilliant frozen facade. The geological youth written across Enceladus's surface tells a story of ongoing renewal and active processes, yet it simultaneously conceals the deeper temporal narrative of planetary evolution that spans geological eras and created the extraordinary conditions that make this small moon one of the most fascinating worlds in the outer solar system. The pristine ice fields reflect sunlight like mirrors, their brightness hiding the shadows of deep time where liquid water has persisted in darkness far longer than complex life has existed on Earth. The comparison between Enceladus's potential seafloor environment and Earth's deep ocean hydrothermal vents provides a framework for understanding how life might emerge and persist in the darkness beneath alien ice, where chemical energy replaces sunlight as the fundamental driver of biological processes. Terrestrial hydrothermal vents create oases of life in the deep ocean through chemosynthetic pathways that derive energy from chemical reactions rather than photosynthesis, supporting complex ecosystems that thrive in conditions of perpetual darkness, extreme pressure, and water temperatures that approach or exceed the boiling point. These environments demonstrate that life can flourish using chemical energy sources that might be available within Enceladus's subsurface ocean. Earth's hydrothermal systems operate through circulation patterns where cold seawater penetrates fractured oceanic crust, becomes heated through contact with magma chambers or recently cooled igneous rocks, and returns to the seafloor carrying dissolved minerals and reduced chemical compounds that provide energy sources for chemosynthetic organisms. The heated water emerges through vent structures that create localized environments with elevated temperatures and concentrations of hydrogen sulfide, methane, carbon dioxide, and various metal sulfides that serve as electron donors and acceptors for metabolic processes. Similar circulation patterns could potentially operate within Enceladus's rocky core, where tidal heating might drive convective flow of ocean water through fractured silicate materials. The chemical signatures detected in Enceladus's plume materials show striking similarities to the compositions found at terrestrial hydrothermal vents, including elevated concentrations of hydrogen sulfide, dissolved metals, and organic compounds that form through water-rock interactions under elevated temperature conditions. The presence of molecular hydrogen in the plumes particularly intrigues astrobiologists because this simple molecule serves as a primary energy source for many chemosynthetic organisms on Earth, including methanogens that produce methane through the reduction of carbon dioxide and sulfate-reducing bacteria that derive energy from the conversion of sulfate to hydrogen sulfide. Theoretical models of Enceladus's seafloor environment suggest that hydrothermal circulation could operate through fracture networks within the moon's rocky core, where tidal flexing creates pathways for fluid flow and generates the temperature gradients necessary to drive convective processes. Unlike Earth's hydrothermal systems, which derive their heat primarily from magmatic activity and radioactive decay. Enceladus's potential hydrothermal circulation would be powered by tidal dissipation and the modest radiogenic heating available within the small moon's rocky component. These energy sources provide continuous but relatively modest heat flow compared to the dramatic thermal outputs of terrestrial mid-ocean ridge systems. The pressure conditions at Enceladus's ocean floor create environments comparable to the deepest hydrothermal vents on Earth, where pressures reach several hundred times atmospheric pressure and create unique chemical equilibrium conditions that affect the stability of different mineral phases and dissolved species. These high-pressure environments favor the formation of certain types of clay minerals, serpentine phases, and hydrated silicates that could serve as catalytic surfaces for complex organic synthesis reactions, potentially creating the molecular building blocks necessary for the emergence of self-replicating chemical systems. Laboratory experiments attempting to simulate Enceladus-like hydrothermal conditions have successfully produced some of the organic compounds detected in the plume materials, confirming that abiotic synthesis pathways can operate under the inferred environmental conditions. High-pressure reactions between dissolved carbon dioxide, hydrogen gas, and various mineral catalysts generate methane, formaldehyde, and simple organic acids at rates that could sustain chemical complexity within the subsurface ocean. However, these experiments have not yet demonstrated the formation of more complex molecules like amino acids or nucleotides that would be required for biological processes similar to those operating on Earth. The energy flux available through potential hydrothermal processes within Enceladus remains uncertain, though theoretical calculations suggest power outputs measured in watts per square meter rather than the kilowatts per square meter available at the most vigorous terrestrial hydrothermal vents. This lower energy density would require any potential biological systems to operate with greater metabolic efficiency than most terrestrial organisms, possibly favoring slow-growing, highly specialized communities that could persist under energy-limited conditions. Such organisms might resemble the extremophile bacteria found in Earth's deepest subsurface environments, where metabolic rates decrease to levels barely above the threshold of detectability. The chemical-reducing conditions inferred for Enceladus's ocean create environments where hydrogen-based metabolism could potentially operate, using molecular hydrogen as an electron donor for carbon fixation processes that convert dissolved carbon dioxide into organic compounds. This metabolic pathway, known as hydrogenotrophic methanogenesis, supports some of the most primitive organisms on Earth and could potentially provide a biochemical foundation for life in hydrogen-rich environments like those that might exist within the subsurface ocean of this distant ice-covered moon. Mineral catalysis represents another potential pathway for complex organic synthesis within Enceladus's ocean, where clay minerals, metal sulfides, and other catalytically active surfaces could facilitate chemical reactions that produce the molecular precursors necessary for biological systems. Iron-sulfur minerals, common products of hydrothermal alteration processes, show particular promise as catalytic surfaces that could promote carbon fixation, amino acid synthesis, and other key reactions in the hypothetical development of prebiotic chemistry within the alien ocean. The temporal stability of hydrothermal processes within Enceladus could potentially provide the sustained chemical energy sources necessary to support long-term biological evolution. Unlike the episodic activity that characterizes many terrestrial hydrothermal systems, tidal heating operates with predictable cyclical variations but continues indefinitely as long as the orbital resonances with other Saturnian moons maintain the eccentric orbit that drives internal heating. This consistency could create stable chemical environments that persist for millions or billions of years, providing the temporal framework necessary for complex evolutionary processes to operate. The isolation of Enceladus's potential hydrothermal systems from external contamination creates experimental conditions that differ significantly from Earth's interconnected ocean basins, where chemical and biological exchange occurs across global circulation patterns. Any life that might emerge within the subsurface ocean would evolve in complete isolation from terrestrial biological influences, potentially developing biochemical pathways, metabolic strategies, and structural organizations that reflect the unique environmental constraints imposed by this particular alien world. The hydrothermal vent analogy provides a scientifically grounded framework for considering the potential habitability of Enceladus's subsurface ocean, while acknowledging the significant uncertainties that remain regarding the actual chemical and physical conditions existing at the interface between liquid water and solid rock within this distant moon. The comparison suggests that life-supporting chemical processes could potentially operate within the hidden ocean, though confirming the presence of biological activity would require direct sampling of the ocean's contents rather than analysis of the processed materials that emerge through the plume systems. The sampling challenge presented by Enceladus's plume system resembles an attempt to understand a complex chemical factory by analyzing only the exhaust emerging from its smokestacks. Where the violent ejection process fundamentally alters the materials being studied and potentially destroys the most fragile evidence of the processes occurring within, each eruption subjects ocean water and dissolved materials to extreme pressure gradients, rapid temperature changes, and phase transitions that could chemically modify or physically destroy delicate molecular structures before they reach the weighting instruments of spacecraft flying through the resulting ice and vapor clouds. The plumes offer tantalizing access to samples from an alien ocean, yet they simultaneously impose severe limitations on the fidelity with which those samples represent the original subsurface chemistry. The explosive decompression that drives plume formation creates conditions similar to those found in terrestrial geysers, where liquid water under pressure suddenly encounters much lower pressure environments and flash boils into steam and ice particles. This process, known as flashing or cavitation, generates temperatures and pressure gradients that can break chemical bonds, alter molecular structures, and create new compounds that didn't exist in the original liquid phase. Simple molecules like water, carbon dioxide, and methane survive this violent transition relatively intact, but more complex organic compounds may fragment, polymerize, or undergo other chemical transformations that obscure their original forms and concentrations. Temperature effects during plume eruption present another source of potential alteration, as materials transition from the relatively warm subsurface environment to the extreme cold of space within seconds or minutes. Rapid cooling could freeze chemical reactions in progress, preserving intermediate species that would normally convert to more stable products under equilibrium conditions. Conversely, the brief heating episode during explosive decompression might accelerate chemical reactions that proceed too slowly under normal ocean conditions, creating molecular species that represent artifacts of the sampling process rather than genuine ocean chemistry. The physical sorting that occurs during plume formation preferentially ejects certain types of materials while retaining others within the subsurface system, creating systematic biases in the composition of ejected samples. Volatile compounds like gases and low boiling point organic molecules escape more readily than dissolved salts and complex macromolecules, potentially creating plume compositions that overrepresent some chemical components while underrepresenting others. Large molecules, fragile molecular complexes, and materials with high boiling points may remain predominantly within the ocean rather than participating significantly in the plume emissions. Ice particle formation during eruption creates additional complications for chemical analysis, as dissolved materials become incorporated into ice crystals through processes that can concentrate some species while excluding others. The crystal structure of water ice accommodates only certain types of dissolved materials, potentially leading to fractionation effects where the ice particles carry different chemical signatures than the original liquid from which they formed. Salt crystals and organic inclusions within ice particles may represent concentrated samples of specific dissolved components rather than representative mixtures of total ocean chemistry. Radiation exposure during the journey from subsurface sources to spacecraft instruments introduces another layer of potential alteration, as energetic particles from Saturn's magnetosphere can break chemical bonds, create free radicals, and initiate reactions that wouldn't occur under the shielded conditions existing within the ocean. The plume materials spend minutes to hours exposed to this radiation environment before reaching the sampling instruments, providing sufficient time for radiation-induced chemistry to alter molecular compositions and create spurious signals that complicate interpretation of the original ocean chemistry. Contamination from the spacecraft itself and from interplanetary space presents ongoing challenges for identifying the pristine signatures of Enceladus's ocean chemistry. Outgassing from spacecraft materials, residual propellant, and accumulated interplanetary dust create background signals that must be carefully subtracted from the measurements to isolate the genuine Enceladus components. The ultra-high vacuum conditions of space mean that even trace amounts of contaminating materials can create detectable signals that might be misinterpreted as evidence of complex chemistry within the alien ocean. The spatial and temporal variations in plume composition create additional uncertainties about how representative individual measurements might be of the overall ocean chemistry. Different plume jets carry distinct chemical signatures, possibly reflecting sampling of different depth layers, residence times, or circulation patterns within the subsurface ocean. Temporal variations correlated with orbital position suggest that tidal stresses influence not only the intensity of plume activity, but also the chemical composition of ejected materials, potentially creating systematic biases that depend on when and where samples are collected. Instrumental limitations of current spacecraft, mass spectrometers restrict the types of molecular analysis that can be performed on plume materials, particularly for complex organic compounds that require high-resolution separation and identification techniques. The instruments aboard Cassini, while remarkably sophisticated for their time, cannot provide the detailed molecular characterization capabilities available in terrestrial laboratories, leaving significant gaps in understanding of organic chemistry complexity and leaving many detected signals ambiguously identified or completely uncharacterized. The brief encounter times available during spacecraft flybys limit the total amount of plume material that can be sampled and analyzed, creating statistical uncertainties that affect the reliability of composition measurements. Unlike terrestrial sampling programs that can collect large quantities of material for detailed laboratory analysis, spacecraft investigations must extract maximum information from the tiny amounts of material that can be captured during high-velocity passes through the plume streams, often at relative speeds measured in kilometers per second. Future missions specifically designed to sample Enceladus's plumes could potentially address some of these limitations through improved instrumentation, multiple sampling opportunities, and possibly sample return capabilities that would allow terrestrial laboratory analysis of collected materials. Advanced mass spectrometers, ion chromatography systems, and molecular identification instruments could provide much more detailed chemical characterization of plume contents, while multiple encounters would enable statistical analysis of temporal and spatial variations in composition. The sampling challenge exemplifies the broader difficulties inherent in studying alien environments through remote sensing and brief spacecraft encounters, where the most interesting and potentially significant discoveries may require direct access rather than indirect measurement through natural emission processes. The plumes provide unprecedented access to samples from an extraterrestrial ocean, yet they simultaneously demonstrate the limitations of studying complex chemical systems through processes that fundamentally alter the materials being investigated. Despite these challenges, the plume sampling approach represents the only currently feasible method for investigating Enceladus's ocean chemistry without the enormous technical and financial commitments required for subsurface drilling or submarine exploration of the hidden sea. The chemical signatures detected in plume materials, even if altered by the sampling process, provide valuable constraints on ocean composition and chemical processes while pointing toward the types of investigations that future, more capable missions might undertake to unlock the remaining mysteries of this alien ocean world. The rhythmic variations in Enceladus's plume activity follow the gravitational choreography of orbital mechanics with mathematical precision, creating a celestial breathing pattern that intensifies and diminishes according to the Moon's changing distance from Saturn during each 33-hour orbital cycle. As Enceladus swings through the closest approach to the giant planet, tidal forces reach their maximum intensity, squeezing and stretching the ice shell with gravitational stresses that open fractures wider and drive more vigorous eruptions from the Tiger Stripe network. The plumes respond like pressure relief valves operating under cyclical stress, their intensity correlating directly with the tidal forces that peak during each orbital periapsis passage. Detailed monitoring of plume activity over multiple orbital cycles reveals systematic patterns in both the total mass flux of ejected material and the spatial distribution of individual jet sources along the Tiger Stripes. During periods of maximum tidal stress, the combined output from all active vents increases by factors of 3 to 5 compared to baseline levels measured during the more distant portions of the elliptical orbit. Individual jets show varying responses to tidal forcing, with some sources demonstrating extreme sensitivity to gravitational stress, while others maintain relatively constant output levels throughout the orbital cycle, suggesting different plumbing configurations or pressure conditions within the subsurface fracture networks. The orbital mechanics governing these variations involve complex interactions between Enceladus's position relative to Saturn, the orientation of the Tiger Stripes with respect to the tidal stress field, and the internal pressure conditions existing within the Moon's fracture systems. Computer models of tidal stress patterns show that the maximum extensional forces occur when Enceladus reaches periapsis, with the Tiger Stripes oriented perpendicular to the Saturn-facing direction, creating optimal conditions for fracture opening and enhanced material ejection. The stress patterns rotate through different orientations as the tidally locked Moon maintains the same face towards Saturn, while the Tiger Stripes maintain fixed orientations relative to the Moon's surface features. Temperature measurements of the Tiger Stripe regions show corresponding variations that follow the same orbital periodicity as the plume activity changes, with surface temperatures rising during periods of enhanced tidal stress and falling during orbital phases when gravitational forces relax. These thermal cycles suggest that tidal friction generates heat directly within the fracture zones, warming the ice and potentially creating more efficient pathways for subsurface material to reach the surface. The temperature variations measure several degrees Celsius, significant changes in the context of the extremely cold surface conditions, but modest compared to the temperature gradients existing between the surface and the subsurface ocean. The chemical composition of plume materials also shows subtle variations that correlate with orbital position, though these changes remain within the measurement uncertainties of current instrumentation and require careful statistical analysis to detect reliably. Some observations suggest that periods of enhanced plume activity carry higher concentrations of dissolved salts and organic compounds, possibly indicating that stronger eruptions access deeper or more chemically evolved regions of the subsurface reservoir systems. Alternative interpretations propose that the apparent compositional variations result from changes in eruption dynamics that alter the efficiency with which different chemical species become incorporated into the ejected ice and vapor. The discovery of orbital control over plume activity provides important constraints on theoretical models of the subsurface fracture network and the pressure conditions existing within chambers that feed the tiger stripe eruptions. Simple models involving direct connection between surface fractures and the global ocean would predict much smaller variations in activity levels, as the vast ocean volume would buffer pressure changes caused by tidal deformation. The observed sensitivity to tidal forcing suggests that intermediate-scale reservoirs or chambers within the ice shell play important roles in controlling eruption dynamics. Storing pressurized material during periods of low tidal stress and releasing it more vigorously when gravitational forces facilitate fracture opening. Resonance effects between the orbital period and internal oscillations within the fracture system could potentially amplify the response to tidal forcing, creating larger activity variations than would result from purely static stress changes. Such resonances might involve pressure oscillations within subsurface chambers, thermal expansion and contraction cycles, or mechanical vibrations within the fracture network that become synchronized with the orbital motion. These dynamic effects could explain why some individual jet sources show particularly dramatic responses to tidal forcing, while others maintain more constant behavior patterns. The phase relationships between tidal stress maxima and peak plume activity reveal information about the response time of the subsurface system to gravitational forcing. Observations indicate that maximum plume intensity occurs approximately coincident with peak tidal stress, rather than showing significant time delays that might be expected if material transport through the fracture network required substantial travel times. This near-instantaneous response suggests that the active plume sources maintain relatively direct connections to pressurized reservoirs that can respond rapidly to stress changes, rather than depending on slow transport processes through extensive fracture networks. Long-term variations in the orbital eccentricity of Enceladus, driven by gravitational perturbations from other Saturnian moons, could potentially create secular changes in average tidal heating rates and plume activity levels over timescales of thousands to millions of years. These variations might explain apparent discrepancies between theoretical predictions of tidal heating based on current orbital parameters and the geological evidence for sustained activity over much longer periods. The orbital system continues to evolve slowly as tidal interactions gradually modify the trajectories of Saturn's moons, potentially creating epochs of enhanced or diminished activity that correlate with variations in the strength of gravitational forcing. The seasonal modulation of plume activity creates opportunities for targeted observation strategies that maximize the scientific return from spacecraft encounters. Future missions could potentially time their closest approaches to coincide with predicted periods of maximum activity, ensuring optimal conditions for plume sampling and chemical analysis. Conversely, observations during periods of reduced activity could provide baseline measurements that help distinguish the effects of eruption dynamics from the underlying chemical signatures of the subsurface ocean. The orbital choreography that controls Enceladus's plume variations demonstrates the intimate connection between celestial mechanics and geological processes, showing how gravitational forces transmitted across millions of kilometers can control the timing and intensity of geological activity on distant worlds. The mathematical precision of these relationships provides a natural laboratory for studying tidal effects on planetary geology, while offering predictive capabilities that could inform future exploration strategies designed to maximize scientific discoveries within the practical constraints of interplanetary mission design. Saturn's gravitational influence reaches across the vacuum to conduct this orbital symphony, where Enceladus dances through its elliptical path while the tiger stripes respond with clockwork precision to the ebb and flow of tidal forces. The plumes rise and fall in rhythm with invisible gravitational currents, their intensity modulated by the same mathematical relationships that govern ocean tides on Earth, but operating in an environment of perpetual cold where ice geysers fountain into the darkness of space with mechanical regularity that has likely persisted for millions of years. The apparent accessibility of Enceladus's subsurface ocean through its spectacular plume system creates a tantalizing illusion that this alien sea lies nearly within reach of current space exploration technology. Yet the reality of sampling limitations reveals how the dramatic ice geysers may simultaneously offer the closest approach to an extraterrestrial ocean while potentially filtering or obscuring the most significant discoveries waiting within its depths. The plumes fountain upward from the tiger stripes like natural sampling systems, ejecting material from realms that would otherwise require complex drilling operations through kilometers of ice, but they operate according to physical and chemical processes that inevitably alter everything they carry toward the surface and into the vacuum of space. The vertical journey from ocean depths to space traverses environments with dramatically different temperature, pressure, and chemical conditions that subject transported materials to a gauntlet of physical and chemical transformations. Liquid water begins its ascent at temperatures approaching 4 degrees Celsius under pressures measuring dozens of atmospheres, conditions that maintain chemical equilibrium and molecular stability for complex dissolved species. As this material rises through fracture networks within the ice shell, decompression causes dissolved gases to exsolve from solution, while decreasing temperatures begin to affect the stability of temperature-sensitive chemical compounds. The final explosive transition from liquid to vapor during plume eruption subjects all transported materials to extreme conditions that can break chemical bonds, alter molecular structures, and create entirely new compounds through high-energy reactions that occur during the microseconds of violent decompression. Organic molecules particularly vulnerable to these processes include complex polymers, large biomolecules, and unstable intermediate species that might provide crucial evidence for biological or prebiotic chemistry within the ocean. The most fragile and potentially most significant chemical signatures may be systematically destroyed during every eruption event, leaving behind only the hardiest molecular survivors to represent the ocean's true chemical complexity. Thermal processing during plume formation creates additional opportunities for chemical alteration as materials experience rapid temperature cycling from ocean conditions through brief heating during explosive decompression to the extreme cold of space within time frames measured in seconds. These thermal shocks can trigger chemical reactions that wouldn't occur under stable temperature conditions, potentially creating spurious molecular signals that represent artifacts of the sampling process rather than genuine ocean chemistry. Alternatively, rapid cooling might freeze ongoing chemical reactions in intermediate states, preserving molecular species that would normally convert to more stable products under equilibrium conditions. The physical separation processes inherent in plume dynamics preferentially eject certain types of materials while retaining others within the subsurface system, creating systematic biases in the composition of ejected samples that may not represent the true chemical diversity existing within the ocean. Volatile compounds escape preferentially during eruption events, while larger molecules, dissolved salts with high boiling points, and particulate materials may remain predominantly within the liquid reservoir. Any hypothetical biological materials, particularly cellular structures or complex biomolecules, would likely be preferentially retained within the ocean rather than efficiently transported through the violent ejection process. Ice crystal formation during eruption creates another layer of chemical processing that alters the composition of ejected materials through fractionation effects that concentrate some dissolved species while excluding others. The crystalline structure of water ice accommodates only specific types of chemical inclusions, potentially leading to systematic underrepresentation of certain molecular classes in the ice particles that reach spacecraft instruments. Complex organic compounds, metal complexes, and other large molecular species may be excluded from ice crystal lattices, remaining in the liquid phase and falling back toward the surface rather than participating in the long-range transport that creates the extended plume structures. The duration of exposure to Saturn's radiation environment during transport from the subsurface to spacecraft instruments provides additional opportunities for chemical modification through radiation-induced chemistry. Energetic particles from Saturn's magnetosphere can break chemical bonds, create reactive free radicals, and initiate cascade reactions that alter molecular compositions over the minutes to hours required for plume material to traverse the space between Enceladus and visiting spacecraft. These radiation effects could systematically destroy evidence of complex chemistry while creating false signals that might be misinterpreted as evidence of sophisticated molecular processes within the ocean. Dilution effects during plume dispersion reduce the concentrations of all chemical species below their original levels within the ocean, potentially decreasing rare or trace compounds to concentrations below instrumental detection limits. The most significant discoveries might involve chemical species that exist at very low concentrations within the ocean but provide crucial evidence for biological or prebiotic processes. The dilution inherent in plume formation and dispersion could render these most important compounds undetectable, even if they exist at biologically significant levels within the subsurface ocean. The temporal and spatial heterogeneity of plume composition creates additional challenges for obtaining representative samples of ocean chemistry, as different eruption events may sample distinct regions or depth layers within the subsurface system. Individual spacecraft encounters capture only brief snapshots of plume composition during specific orbital and tidal conditions, potentially missing chemical signatures that appear only under certain environmental conditions or during particular phases of geological activity. The most interesting chemistry might occur during periods or locations that remain inaccessible to current sampling strategies. Instrumental limitations of spacecraft-based analytical systems impose further constraints on the types of chemical analysis that can be performed on plume materials, particularly for identifying complex organic compounds or detecting potential biological signatures that might require sophisticated separation and identification techniques. The mass spectrometers and other analytical instruments carried by current and planned missions, while remarkably capable given their size and power constraints, cannot provide the comprehensive molecular characterization capabilities available in terrestrial laboratories equipped with advanced chemical analysis systems. The promise of easy access to an alien ocean through natural plume systems has guided mission planning and scientific expectations. Yet, the recognition of sampling limitations highlights the need for more direct exploration approaches that could bypass the chemical and physical processing imposed by explosive eruption events. Future missions might need to consider drilling through the ice shell, deploying autonomous underwater vehicles within the ocean, or developing advanced in-situ analysis capabilities that could characterize ocean chemistry without relying on the natural but potentially misleading sampling provided by plume emissions. The false promise embedded within Enceladus's spectacular plume displays reflects a broader challenge in planetary exploration, where the most accessible phenomena may not provide the most accurate information about the environments being studied. The ice geysers create compelling visual evidence of geological activity and offer unprecedented access to subsurface materials, yet they simultaneously impose systematic limitations on the fidelity with which those materials represent the chemical and potentially biological processes occurring within one of the solar system's most intriguing hidden oceans. The plumes continue their rhythmic eruptions, carrying samples from alien seas across millions of kilometers of space to waiting instruments. Yet each spectacular fountain event represents both an opportunity and a limitation, providing access while potentially concealing the most significant discoveries beneath layers of chemical and physical processing that transform ocean chemistry into something fundamentally different during its violent journey from liquid sea to cosmic vacuum. Beyond Enceladus, other ice-covered moons scattered throughout the outer solar system exhibit their own patterns of geological activity and potential plume emissions, each world telling a distinct story about the conditions that might sustain subsurface oceans and the mechanisms through which hidden seas might announce their presence to orbiting spacecraft and telescopic observers. Europa, Jupiter's fourth-largest moon, shows evidence of water vapor plumes that emerge sporadically from fractures near its south pole. Though these eruptions appear less vigorous and more intermittent than the continuous displays that characterize Enceladus's tiger stripe activity, the Europa plumes, when detected, reach heights of only 100 to 200 kilometers above the surface, modest compared to Enceladus's 500-kilometer fountains, suggesting different pressure conditions or eruption mechanisms operating within Jupiter's gravitational environment. The detection of Europa's plumes required years of careful observation and sophisticated image processing techniques that could identify the faint signatures of water vapor against the bright background of reflected sunlight from the moon's ice-covered surface. Unlike Enceladus's dramatic and easily observable eruptions, Europa's plume activity appears episodic and localized, occurring primarily during the moon's closest approach to Jupiter when tidal stresses reach maximum intensity. The irregular timing and lower intensity of these eruptions suggests that Europa's subsurface ocean may be more deeply buried beneath its ice shell, or that the fracture networks connecting ocean to surface operate under different pressure and temperature conditions than those found within Enceladus. Triton, Neptune's largest moon, presents evidence for nitrogen plumes rather than water-based emissions, creating geysers that reach heights of several kilometers above the surface through mechanisms driven by solar heating of subsurface nitrogen deposits rather than liquid water reservoirs. These nitrogen fountains operate through sublimation processes where solid nitrogen transitions directly to gas phase when warmed by Neptune's distant sunlight, demonstrating that plume activity can occur through various mechanisms beyond the water-based systems observed on Enceladus and Europa. Triton's plumes carry dark particles thought to originate from organic compounds or carbon-rich materials mixed with the nitrogen ice, creating distinctive dark streaks that extend for hundreds of kilometers across the moon's predominantly bright surface. Io, Jupiter's volcanically active moon, produces the most spectacular plume displays in the solar system through sulfur dioxide emissions that reach heights exceeding 400 kilometers above the surface, driven by volcanic processes and tidal heating effects that create internal temperatures sufficient to maintain molten silicate lavas. Io's plumes differ fundamentally from those observed on ice moons, originating from high-temperature volcanic processes rather than liquid water systems. Yet they demonstrate the variety of mechanisms through which subsurface processes can create dramatic atmospheric phenomena that extend far beyond planetary surfaces into the vacuum of space. Ganymede, Jupiter's largest moon, shows indirect evidence for a subsurface ocean through magnetometer measurements that indicate conducting fluids within its interior, though no direct plume emissions have been detected from this massive world. The absence of observable plumes, despite probable ocean conditions, suggests that ice shell thickness, internal pressure conditions, or fracture network development may prevent subsurface materials from reaching the surface through eruption processes. Ganymede's example demonstrates that subsurface oceans may exist without creating the spectacular plume displays that make other worlds so visually compelling. Callisto, the outermost of Jupiter's large moons, similarly shows magnetic evidence for possible subsurface liquid water reservoirs, yet maintains a heavily cratered surface that shows little evidence of recent geological activity or plume emissions. The contrast between Callisto's ancient, inactive appearance and the dynamic surfaces of Europa and Enceladus illustrates how subtle differences in orbital position, internal structure, or thermal evolution can determine whether subsurface oceans remain hidden beneath inactive ice shells or announce their presence through dramatic geological phenomena. Titan, Saturn's largest moon, possesses surface lakes and rivers of liquid methane and ethane rather than water-based plume systems, creating a fundamentally different type of volatile cycling that operates through atmospheric processes rather than subsurface eruptions. Titan's dense atmosphere and active methane cycle demonstrate alternative pathways for creating dynamic surface and atmospheric phenomena on worlds with subsurface liquid reservoirs, though in this case, the liquids exist at the surface rather than hidden beneath ice shells. The diversity of plume phenomena across different ice moons reflects the varying environmental conditions, internal structures, and evolutionary histories that characterize worlds in the outer solar system. Tidal heating intensity, ice shell thickness, ocean salinity, internal pressure conditions, and fracture network development all influence whether subsurface oceans remain hidden or create observable surface phenomena. The different plume characteristics observed on various worlds provide natural experiments for understanding the physical processes that govern volatile transport and eruption dynamics under the diverse conditions existing throughout the outer solar system. Comparative studies of plume activity across multiple worlds reveal systematic relationships between orbital parameters, internal heating rates, and eruption characteristics that help constrain theoretical models of subsurface ocean dynamics and surface-ocean interaction processes. Europa's position within Jupiter's intense radiation environment creates different chemical conditions than those existing around Saturn, while the varying distances from their respective primary planets create different tidal heating regimes that affect internal temperature distributions and fracture network development. Future comparative planetology studies could potentially identify additional plume-active worlds through systematic surveys of ice moons using advanced infrared telescopes and spacecraft equipped with sensitive particle detectors. The recognition that multiple worlds exhibit plume activity suggests that such phenomena may be common rather than exceptional, indicating that subsurface oceans and the geological processes that connect them to surface environments represent widespread characteristics of ice-covered worlds throughout the outer solar system. The variety of plume systems operating on different worlds demonstrates that each ice moon represents a unique experiment in the physics and chemistry of subsurface ocean maintenance and surface expression. Enceladus, Europa, Triton, and other plume-active worlds each provide different perspectives on the range of conditions under which volatile emissions can occur, the mechanisms that drive such activity, and the chemical signatures that result from these processes. Each moon maintains its own relationship with plume formation and ocean accessibility, creating a diverse catalog of natural laboratories where different combinations of orbital mechanics, internal heating, chemical composition, and geological structure produce varying degrees of surface activity and subsurface ocean expression. The plumes rising from these distant worlds carry messages written in languages of ice, vapor, and dissolved chemistry, each telling stories shaped by the unique environmental conditions existing within these frozen realms scattered across the outer reaches of our solar system. The patient search for definitive evidence of biological processes within Enceladus's subsurface ocean will likely require future missions capable of penetrating the ice shell directly rather than relying solely on the chemically and physically processed materials that emerge through the plume systems, where violent eruption processes and extended exposure to space radiation may systematically destroy or alter the most fragile molecular signatures that could indicate the presence of life. Current and planned spacecraft missions represent important steps toward understanding ocean chemistry and geological processes. Yet they operate within fundamental limitations imposed by remote sensing techniques and brief flyby encounters that capture only glimpses of complex chemical systems operating in environments vastly different from any found on Earth. The development of ice-penetrating probes represents one of the most challenging technical endeavors in planetary exploration, requiring systems capable of melting through kilometers of solid ice while maintaining communication links, power generation, and scientific instrumentation under extreme cold conditions and crushing pressures. Cryobots designed for such missions must carry sufficient energy sources to melt through ice depths that may reach 25 kilometers in some regions of Enceladus, while simultaneously preserving internal temperatures compatible with sensitive scientific instruments and electronic systems. The thermal management challenges alone require innovative engineering solutions that balance heat generation for ice penetration against heat conservation for instrument survival. Communication through solid ice presents additional technical obstacles, as conventional radio signals cannot penetrate effectively through kilometers of frozen water, requiring either fiber optic cables deployed during descent or relay systems positioned at intermediate depths to maintain contact with surface assets and eventually with Earth-based mission control centers. The mechanical stresses imposed by ice refreezing behind a descending probe could sever communication links or trap the vehicle before it reaches its intended destination within the subsurface ocean, creating mission failure scenarios that must be addressed through redundant systems or alternative exploration strategies. Contamination prevention protocols for direct ocean access missions require unprecedented levels of biological cleanliness to avoid introducing terrestrial microorganisms into potentially pristine alien environments, while simultaneously ensuring that any detected biological signatures represent indigenous processes rather than contamination from Earth-based sources. Planetary protection requirements for such missions exceed even the stringent standards applied to Mars exploration, demanding sterilization procedures that must eliminate all viable terrestrial life forms without damaging the sensitive instruments required for detecting alien biological activity. The contradiction between thorough sterilization and instrument sensitivity creates engineering challenges that may require entirely new approaches to spacecraft design and biological cleanliness verification. Autonomous underwater vehicles designed for operation within Enceladus's ocean must function in environments where direct human control becomes impossible due to communication delays measured in hours and environmental conditions that preclude real-time intervention if problems develop during exploration activities. These systems require sophisticated artificial intelligence capabilities that can navigate unknown underwater terrain, identify scientifically interesting features, collect appropriate samples, and respond to unexpected situations without human guidance. The development of such autonomous systems represents one of the frontier challenges in robotics and artificial intelligence applications to space exploration. Sample collection and analysis within the alien ocean environment requires miniaturized laboratory systems capable of performing sophisticated chemical and potentially biological analyses using instruments that must function reliably under high pressure, low temperature, and complete darkness conditions. Current laboratory techniques for detecting biological signatures, identifying complex organic molecules, and characterizing cellular structures require substantial analytical equipment that must be redesigned for operation in the compact, power-limited, and environmentally extreme conditions that characterize subsurface exploration missions to distant ice-covered worlds. The search for biological signatures within Enceladus's ocean must account for the possibility that any life forms that might exist in this environment could differ fundamentally from terrestrial organisms in their biochemistry, cellular structure, metabolic pathways, and reproductive strategies. Alien life forms adapted to high-pressure, permanently dark, chemically unique environments might not produce the molecular signatures typically associated with terrestrial biological processes, requiring exploration missions to cast wider investigative nets that could detect biological activity based on more general principles rather than specific molecular targets derived from Earth-based biological experience. Alternative biochemistries potentially operating within Enceladus's ocean could involve silicon-based molecular structures, exotic amino acid sequences, non-DNA genetic systems, or metabolic pathways that utilize chemical energy sources unavailable in terrestrial environments. The detection of such alternative biological systems would require analytical approaches that focus on general characteristics of biological organization, such as information storage and transfer, metabolic energy conversion, and self-replication, rather than searching for specific molecules like DNA, proteins, or lipids that characterize terrestrial life forms. Long-term monitoring programs could potentially detect biological signatures through systematic observation of chemical changes within the ocean environment over seasonal, annual, or longer timescales that might indicate biological metabolism, population dynamics, or ecosystem-level processes. Such monitoring would require persistent presence within the alien ocean rather than brief sampling missions, demanding exploration systems capable of operating autonomously for years or decades while maintaining communication links and continuing to collect scientifically valuable data under the harsh conditions existing within this distant subsurface environment. The integration of multiple exploration approaches, including plume analysis, ice penetration, ocean exploration, and long-term monitoring, could provide complementary perspectives on ocean chemistry and potential biological activity that overcome the individual limitations inherent in each technique. Coordinated missions combining orbital observation, surface operations, and subsurface exploration could create comprehensive investigation programs that maximize the probability of detecting biological signatures while minimizing the risks associated with any single exploration approach. International collaboration on Enceladus exploration missions could pool the technical expertise, financial resources, and scientific capabilities necessary to address the extraordinary engineering challenges involved in direct ocean access while sharing the scientific returns among global research communities. The complexity and cost of such missions may exceed the capabilities of individual space agencies, requiring cooperative approaches that combine the strengths of multiple nations and organizations to achieve exploration objectives that remain beyond current technical and financial reach. The timeline for achieving direct ocean access capabilities extends decades into the future, requiring sustained investment in technology development, mission planning, and scientific preparation that must persist through multiple political and economic cycles while maintaining focus on long-term exploration objectives. The development of ice-penetrating probes, autonomous underwater vehicles, and miniaturized analytical laboratories represents multi-decade research and development programs that require consistent support and incremental progress toward increasingly ambitious exploration capabilities. The patient search for life within Enceladus's hidden ocean continues through the systematic development of increasingly sophisticated exploration capabilities. Each technological advance bringing direct access slightly closer, while current missions provide the baseline understanding necessary to design effective future exploration strategies. The ocean waits beneath its frozen shell, preserving whatever chemical and potentially biological secrets it may contain until human technology develops sufficient capability to unlock the mysteries of this alien sea that has remained hidden in darkness since the formation of the solar system. Enceladus continues its ancient orbital dance around Saturn with mathematical precision, completing each elliptical circuit in 33 hours and 18 minutes while maintaining the same ice-covered hemisphere, perpetually facing the giant planet's stormy atmosphere. A gravitational partnership that has persisted for billions of years and will continue for billions more as long as the solar system maintains its current configuration. The small moon follows its prescribed path through the vacuum with clockwork regularity, its trajectory shaped by gravitational forces that operate according to fundamental physical laws unchanged since the formation of planetary systems around young stars throughout the galaxy. Saturn's immense bulk continues to knead Enceladus through tidal forces that flex the rocky core and ice shell with each orbital passage, generating the internal heat that maintains liquid water in realms that should remain frozen at the temperatures existing in the outer solar system. The tiger stripes persist in their patient exhalations, opening and closing with tidal rhythms that correlate precisely with orbital mechanics, while ejecting samples of the hidden ocean into space through fountains that may have operated continuously for millions of years before human instruments arrived to detect and measure their chemical compositions. Each eruption cycle carries material from depths of 20 to 40 kilometers beneath the surface, where liquid water has circulated in darkness since before complex life appeared on Earth, preserving chemical conditions and possibly biological processes in isolation from solar radiation and atmospheric influences that shape surface environments on terrestrial worlds. The plume activity varies with orbital position according to patterns that spacecraft observations have now documented through hundreds of measurement cycles, creating a database of eruption characteristics that reveals systematic relationships between gravitational forcing and geological response on worlds where tidal heating provides the primary energy source for maintaining geological activity. These variations continue with mechanical regularity, intensifying during closest approach to Saturn and diminishing during the more distant portions of each elliptical orbit, demonstrating how celestial mechanics control geological processes across scales ranging from individual fracture systems to global patterns of heat flow and volatile transport. Deep within the moon's interior, convective circulation patterns driven by tidal heating continue to transport dissolved minerals, organic compounds, and potentially biological materials between the rocky seafloor and the base of the overlying ice shell, creating chemical gradients and mixing processes that have operated for geological epochs while slowly modifying ocean composition through interactions between liquid water and silicate minerals. The circulation patterns respond to tidal forcing with cyclical variations that modulate heat transport efficiency and chemical exchange rates, creating temporal variations in ocean chemistry that occur on timescales ranging from hours to millions of years, depending on the specific processes involved. The subsurface ocean maintains its liquid state through the delicate balance between tidal heating input and conductive heat loss through the overlying ice shell, a thermal equilibrium that has apparently persisted through major changes in the solar system's orbital architecture, while other worlds experience dramatic climate transitions or complete loss of surface volatiles. Computer models suggest that this thermal balance could continue indefinitely as long as orbital resonances with other Saturnian moons maintain the eccentric orbit that drives internal heating, creating one of the most stable aquatic environments in the solar system, despite existing in the frozen realm beyond the asteroid belt. Chemical processes within the ocean continue according to thermodynamic and kinetic principles that operate identically throughout the universe, creating molecular complexity through pathways that depend on the specific temperature, pressure, and compositional conditions existing within this particular alien sea. The organic synthesis reactions detected through plume analysis represent ongoing chemical evolution that may have been operating for billions of years. slowly building molecular complexity through abiotic pathways that could potentially lead toward the emergence of self-replicating systems or alternative forms of chemical organization not yet imagined by terrestrial biochemistry. The ice shell covering the global ocean continues its own slow evolution, with surface features forming and disappearing over geological timescales, while the overall thickness and thermal structure adjust to changes in internal heat production and orbital forcing. New fractures develop along stress concentration zones, while older features become buried beneath accumulations of fresh ice deposited through plume fallout and sublimation redeposition cycles that operate continuously across the Moon's surface. The geological processes that created the current tiger stripe configuration will eventually be replaced by new patterns of fracturing and volcanism as internal conditions evolve and tidal stress patterns shift in response to orbital evolution. Future observations by increasingly sophisticated spacecraft and telescopic systems will continue to refine understanding of the chemical and physical processes operating within Enceladus, while searching for evidence of biological activity that might indicate the presence of life within the subsurface ocean. Each new measurement adds incremental knowledge to the growing database of information about this remarkable world, while revealing additional complexities and mysteries that require further investigation through increasingly capable exploration missions and analytical techniques. The small moon serves as a natural laboratory for studying the physics and chemistry of subsurface ocean maintenance, tidal heating processes, and volatile transport mechanisms that operate throughout the outer solar system on worlds where solar heating provides insufficient energy to drive geological activity or maintain liquid water reservoirs. The lessons learned from Enceladus inform understanding of similar processes operating on Europa, Ganymede, Callisto, Titan, and other ice-covered worlds that may harbor hidden seas beneath their frozen surfaces, creating a comparative framework for understanding ocean worlds as a common phenomenon in planetary systems. Enceladus orbits through space carrying its precious cargo of liquid water and dissolved chemistry like a cosmic preserve jar, maintaining conditions that might support life or complex chemistry in an environment completely isolated from terrestrial influences and sustained entirely through gravitational and chemical energy sources that operate independently of solar radiation. The Moon continues its patient circulation around Saturn, while internal processes continue their slow chemical evolution in darkness, creating and maintaining one of the most intriguing environments in the solar system, where the fundamental questions about life's occurrence and distribution throughout the universe might eventually find answers. The orbital mechanics that control this small world's geological activity will continue operating with mathematical precision for billions of years, ensuring that the subsurface ocean and its associated plume systems persist as long as the current satellite system configuration remains stable around Saturn. Enceladus maintains its secrets beneath layers of ice and darkness, while offering tantalizing glimpses of its hidden chemistry through the ghostly plumes that rise like frozen prayers into the cosmic void, carrying messages from an alien ocean in languages of ice and vapor that human science continues to learn how to read and interpret. Far beyond the warmth of the inner solar system, where Earth's blue oceans reflect sunlight and life flourishes in abundance, Enceladus drifts through the perpetual twilight of Saturn's realm like a distant beacon of possibility, its brilliant ice surface gleaming with reflected light from the giant planet's golden atmosphere while concealing an entire ocean world beneath its frozen shell. The small moon has become a symbol of the unexpected complexity that exists in the cold outer reaches of our solar system, where conventional wisdom suggested that only dead, frozen worlds could survive at such distances from the sun's life-giving warmth. The tiger stripes continue their ancient rhythm, breathing ice and vapor into the vacuum with each tidal pulse, their eruptions now reduced to whispers in the cosmic silence as Saturn's gravitational influence wanes during this distant portion of the orbital cycle. The plumes that earlier rose hundreds of kilometers above the surface now fountain with gentler intensity, their gossamer streams catching and scattering the faint light that filters through Saturn's ring system to create ephemeral displays of crystalline beauty that fade quickly into the surrounding darkness. Each ice particle follows its own ballistic trajectory away from the surface, some falling back to create new deposits on the ancient plains, while others escape entirely to join the tenuous E-ring that encircles Saturn like a ghostly reminder of ongoing geological activity. Deep within the moon's interior, the hidden ocean continues its patient circulation in complete darkness, its currents driven by thermal gradients and tidal forces that operate according to physical laws unchanged since the formation of the solar system. The liquid water maintains its chemical equilibrium with dissolved salts and organic compounds while preserving whatever secrets it may contain about the potential for life to emerge and persist in environments far removed from solar heating and photosynthetic processes. The ocean sleeps beneath its ice ceiling, sustaining chemical reactions and molecular interactions that proceed with glacial slowness through geological time. The surface ice fields stretch unbroken toward distant horizons, their crystalline plains marked only by the subtle ridges and fractures that record millions of years of tidal stress and geological evolution. Crater rims softened by eons of sublimation and redeposition create gentle undulations in terrain that appears smooth and featureless from great distances, but reveals intricate patterns of stress and renewal when examined at higher resolution. The ice reflects starlight and Saturn shine with mirror-like efficiency, creating a world that glows with borrowed illumination while remaining perpetually cold enough to freeze the atmosphere of Earth into solid layers. Saturn dominates the sky above Enceladus's synchronously locked hemisphere, its banded atmosphere displaying the same face toward the small moon that has gazed upward for billions of years through the same gravitational embrace that generates the tidal heating responsible for maintaining geological activity. The giant planet's rings stretch across the heavens in impossible arcs that dwarf any terrestrial conception of celestial architecture, their countless ice particles and rocky fragments creating structures of mathematical precision that demonstrate gravitational physics on scales that encompass entire worlds within their circumference. The cosmic silence that envelops this distant realm permits only the faintest sounds, the occasional crack of thermal expansion in surface ice, the whisper of subliming water vapor, and the nearly inaudible hiss of plume particles settling back to the surface after their brief journey through the vacuum. No wind disturbs the pristine ice fields. No weather systems create clouds or precipitation. No biological processes generate the complex soundscapes that characterize terrestrial environments. Enceladus exists in a silence so profound that it represents the baseline quiet of deep space, interrupted only by the mechanical processes of geology and orbital dynamics. The moon's geological processes continue with patient persistence, operating on timescales that dwarf human history while maintaining the delicate balance of forces that sustains liquid water in one of the least likely environments imaginable for such a phenomenon. Tidal heating, orbital resonances, and chemical equilibrium maintain their ancient dance while slowly evolving through processes that will reshape this world's characteristics over millions and billions of years yet to come. The small moon carries its burden of mystery through space with mechanical precision, neither hurried nor delayed by human curiosity about its potential significance in understanding life's distribution throughout the universe. In the profound stillness of the outer solar system, where temperatures approach absolute zero and radiation levels barely exceed the cosmic background, Enceladus maintains its vigil as one of the solar system's most intriguing worlds. Its subsurface ocean preserves conditions that might harbor life or complex chemistry while remaining completely isolated from terrestrial contamination and influences, creating a natural laboratory where fundamental questions about biology and chemistry operate according to physical principles that transcend the specific conditions existing on any individual world. The ice moon drifts onward through its prescribed orbit, carrying its secrets through the cosmic night, while human science slowly develops the capabilities necessary to unlock the mysteries preserved beneath its frozen surface. Time moves differently in these remote realms, where geological processes operate over millions of years and chemical evolution proceeds through pathways that may eventually lead toward discoveries that reshape understanding of life's occurrence throughout the galaxy. Enceladus sleeps in Saturn's gravitational embrace, its hidden ocean preserved in darkness while the plumes continue their patient exhalations into space, carrying chemical messages from an alien sea that has maintained its liquid state since before the emergence of complex life on Earth, waiting in the frozen silence of the outer solar system for humanity to develop sufficient wisdom and capability to read the stories written in languages of ice and dissolved chemistry within its depths.